Hello, Chemistry 11. This is Mr. Chan. And today's lesson, we are going to be talking about another practical aspect using mole calculations. Now, last day we had talked about molarity, where we were determining the formula, determining the concentration of certain solutions using moles over liters. Today, what we're going to do is we're going to work on how do we determine the formula of a compound. Now, back in grade 9, grade 10, you remember from chemical naming, you would use, hand holding like what I had talked about before in class. But how are we going to determine the formula using numbers and calculations? And that's where the mole concept is also going to be applied. Now, there's two types of formulas that we talk about. One of them is called the empirical formula. Empirical formula is the simplest whole number ratio of atoms in a compound. So let's say the simplest formula. So for example, let's say we have C4H4. The empirical formula would be CH because the ratio, even though it's 4 carbons and 4 hydrogens, the ratio is 1 to 1. So the empirical formula is the simplest whole number ratio. The second example that I show you up here is C2O4. So there's 2 carbons and 4 oxygens. The empirical formula would be CO2. Okay, now, how does one find the empirical formula? So there are 4 steps to it. It says, number 1, find the mass of each element in the compound, convert each element into moles, divide each answer from number 2 by the smallest value to get a ratio of atoms. Note, if you don't get a whole number ratio, for example, 1.33, etc., then you will need to multiply that value to get a whole number. And I'll talk about this a little bit later on. So I'm just going to put a little star here. And then you write the empirical formula. Now, so what I have is I'm going to give you 3 examples for you to take a look at. So example number 1, you can copy this down into your notes. It says, what's the empirical formula for glucose, C6H12O6? The answer would be C1H2O1. Why? Is because you have 6 carbons, 12 hydrogens, and 6 oxygens. The simplest ratio is 1 to 2 to 1. Now, here's one where we might need to use the 4 steps. It says a compound contains 71.65 grams of chlorine, 24.27 grams of carbon, and 4.07 grams of hydrogen. Calculate the empirical formula of this compound. Now, what I'm going to do is I'm going to make it into a little bit of a table. Okay, so what we have here is I'll draw a table here. Okay. And how much space? Oh, perfect. Okay. And I'm just going to fill in this table. 1, 2, 3. Okay. So what we have is we have our element. We have carbon, hydrogen, oxygen. And then what we have is we have the mass. Here we have the mole. Here we have the ratio. Okay. Now, the mass, the mole, the ratio equates to the first step, oopsie, the second step, and the third step that we had talked about in our notes. So step 1, step 2, step 3. Okay. So if we take a look at this, so the mass here of, oops, it's not oxygen, sorry, it is chlorine. Whoopsie. So we have carbon is 24.27, hydrogen is 4.07, and chlorine would be 71.65. Now, what you want to do is you want to, let's see, whoopsie, find the number of moles first, okay? So in this case, doesn't matter which method you use to try to find moles, okay? Some of you might go, okay, you have 24.27 grams all over X mole is equal to 12.0 grams over 1 mole. You can do that. Okay, some of you might go 4.07 grams times 1 mole all over 1.0079. Okay, and then some of you might just go 71.65 grams divided by 35.45 grams. Okay, now I'm just going to modify the little line here because I might need a little bit more space. Okay, let's redraw this here. So regardless of which value, which way you use, okay, what you should get is 24.27 divided by 12. So I get 2.2023. 1.07 divided by 1.0079. I got 4.038. And then 71.65 divided by 35.45. So I get 2.021. Okay. Now, that's to find the number of moles. Now, it says in step number 3, if we take a look at my notes, it says divide each answer from number 2 by the smallest value to get a ratio of atoms. So in this particular case, when you look at your example here, 2.021 is your smallest value. Okay, so I'm just going to highlight it. So for step 3, for the ratio, what you want to do is you divide every number by the smallest number. So here, 0.023 divided by 2.021, 4.038 divided by 2.021, and 2.021 divided by 2.021. And so I'm just going to highlight it in yellow, 1, 2, and 3. So what do we get for our ratio? If we take a look, it is 2.023 divided by, so I get 1.009. In this case, 4.038 divided by 2.021. I get 1.998. And in this case, here I would get 1.00. Now, that was step 3. Step 4, it says write the empirical formula. So step 4, the empirical formula would be, if I have it here, C1.009, H1.998, and O1.000. I can round it off, and I have C1, H2. Why do I keep on saying O? Cl, and then it would be Cl 1.0. Okay, Cl. Okay. All right. Oops. Something's going on here. 1.00. All right. So that is how you would determine the empirical formula. All right, ladies and gentlemen. Now, So take a look at this, and then you notice I'm following the 4 steps. All right. Now, what I want to do is I want to try, let's do the last example here. So here we have 1. Okay. Now, it says a 100-gram compound contains 48.64 grams of carbon, 8.16 grams of hydrogen, and the rest is oxygen. What is the empirical formula? Now, in this particular case, again, let's set up our table. And again, we have our elements. We have carbon, hydrogen, oxygen. We have our mass. Okay. Now, in this case, it'd be 48.64. Here is 8.16. And the rest is oxygen, which is, in this case, which would be 43.20. Now, again, how did I get that number? Is because there's 100 grams of the compound. And some of it is made up of carbon and hydrogen. And the key word is the rest of it is oxygen. So that's how I got the answer of 43.20. So what I'm going to ask you to do right now is, can you find step 2, the moles, and step 3, the ratios? And then what you can do is pause the video right here. And then when you are done, unpause, and then we'll continue on. Welcome back. And so what you see right now is I've done the calculations and I've gotten my ratios of carbon, hydrogen, and oxygen to be 1.501, 3.02, and 1.00. Now, you notice the number here, especially the 1.5. Now, it's not as clean as the numbers up here. So when you have a number that's not very clean, like a 1.5, what you want to do is do what I put here in a little dot. It says, if you don't get a whole number ratio, get a ratio. If you don't get a whole number ratio, get a ratio. You will need to multiply that value to get a whole number. So in this particular case, so let's say you have 1.5. You don't know if you can round up or round down. So what you have here is, in this case, you want to multiply it by 2. So you get 3.002, 6.04, and then you have 2.00. Now, notice these numbers are a little bit cleaner than the 1.5. And so what you can do now is, once these numbers are relatively clean, I call clean, you could write the empirical formula. So that would be C3H6O2. Okay. Now, if 2 doesn't work, then you can try 3. If 3 doesn't work, you try 4. If 4 doesn't work, you can try 5. Okay. Now, a couple of things I would like you to be aware of. Notice here, first of all, if we go back to our other example, when I found the number of moles for hydrogen, I divided it by 1.0079, and chlorine, I divided it by 35.45. Some of you might remember and say, Mr. Chan, isn't hydrogen and chlorine diatomic? So why can't we divide it by 2, or divide it by, for hydrogen, divide it by 2. For chlorine, we divide it by 71. And again, because we're focused on just the hydrogen atom and the chlorine atom. That's the first thing. Second thing is, notice the number of sig figs. What I'm doing is I'm carrying the majority of sig figs, either 3 or 4 sig figs, all the way through my calculations. Okay? And the only time I round is at the very end. And that's what I would recommend when you are doing this, is that when you are doing these calculations, carry at least 3 to 4 sig figs through the mass, the mole, the ratio, and the only time you round is at the very end. Now, the last thing that some of you might say is, Mr. Chan, when will we know when to multiply it by 2 or 3 or 4? And one of the hints is actually found in your textbook. So if you take a look at your textbook, and if you take a look on page 112, they give an example and they get something similar. It says in the answer, it's 1.0 and 1.49, okay? And if you take a look, it says, if you take a look in the reading, it says there are 1.49 moles of oxygen atoms for every mole of iron atoms in the compound. The formula could be written as Fe1O1.49. However, because both atoms are believed to combine in whole number ratios, we multiply both numbers by some whole number. Now, you might say, okay, but when do we determine if the number is whole? And it says here in the last example, 2.98 was rounded to 3, but 1.49 was not considered a whole number. Neither 1.49 nor 2.98 is exactly a whole number. So when can you assume that the number should be rounded to a whole number? Take a minute and take a look at what it says here about the sources of uncertainty and what determines whether you round or not. Now, in this particular case, it's basically a judgment call. Do you think there's significant error, if there's enough error for rounding or not? So they say here, it says in example 4.13, 2.98 was rounded to the whole number 3. Okay. Okay, why? Is because when 2.98 is rounded to 2 digits, you get 3. All right, so it's like when you go shopping, you see the price tag, it says $2.99. You say, okay, it's basically $3. Okay, but if you get 1.5 or something similar, it's very difficult to round it up or down. So ultimately, it's a judgment call, and that's something that you will get used to with extended practice. All right, folks, thank you very much. Have a good day.